Mic check. Mic check. Hello. Hey, how's it going? Interesting flashback. My first talk at any kind of West Coast conference was a Puppet Comp 4 or 5 years ago, and Kelsey was the guy that introduced me on my first serious talk with Project Razor. So it's kind of a little bit of nostalgia. I'm a little misty-eyed because of Kelsey. I love you too, man. Okay, so I'm Nick Weaver. I work for Intel. I previously worked for VMware, and I previously worked for a company called EMC that does some storage things. And right now I work with a team called SCIX. We do kind of prototyping, concept work, software with hardware in the cloud space. And right now we're really excited about the stuff that CoreOS is doing around containers and around distributed consensus and configuration management and operational stuff. And so I'm going to cover kind of an Intel perspective with what we've been playing with this whole new evolving ecosystem and some of the things we've discovered and kind of where we think things could go with this whole thing. But first, I want to talk about this. This is us right here. In human history, some of us produce, some of us consume. And this is how it works. And I know we're all technologists in here, and I'll talk about that in a second. But in history, as we go through, we've produced things that scale using machinery, using lots and lots of labor, using unethical or immoral ways with slavery. But ultimately, it was the evolution of machines that changed everything. We had the ability to produce a lot more of something, and this in turn allowed us to consume more. For example, at one point in time, only the biggest mansions or manors would have a machine that would wash clothes. And then one day, you could open a Sears catalog and buy it. And now, it's a common thing in almost everywhere, every single house you go to. And the machines got bigger and better, and we got smarter at building them, and mechanical engineering became a thing. And we produced more things with less human effort, and we consumed more. Then we consumed even more when computing machines arrived. And the computing machines themselves actually changed the way we did a lot of very simple tasks. And the biggest way I like to point this out is, who's got a cell phone in the room? That's a really dumb question. Believe it or not, every once in a while I see a hand not go up. That question was so easy, nobody even raised their hands. They're like, obviously, wasting my time. Okay, so the thing is, I like to think about 10 years ago, if I wanted to go visit someone, what did I have to have in another state? I had to go buy a map. You guys know what a map is? Some of you are pretty young. It was a laminated, fold-out, flip thing that was about this wide. And it would take you how to get from one place to another looking at a highway system. And if you moved your finger on it, the map didn't move. You had to actually pick it up. I know, this is probably hard to understand. And the crazy thing is, if you were driving on the highway, you thought you were going the right direction, and you needed to figure out where you were, could you do it in the car? No. You had to pull over, unfold the map, and figure out where you were in the world. And so the production of location was very different 10 years ago. Now my daughter, who's 10, on her iPad, can click on it and instantly know where she is in the world. And so we produce location maps, where we are, in such a much more efficient manner now using computing. It's crazy. We've gotten down to where I can click something, and the efficiency of that is so important. And we actually at Intel love to talk about this thing called Jevons paradox. And it's an old, not really too old, but it's this proposition that the more you make something easy to consume, the easier something is to consume, it actually causes people to want more of it. And so the idea there is people should think, hey, if I make it harder to achieve something, harder to do something, then I have access to it, and people have to go through me, and then I own the market. When in reality, if you actually make things easier to consume, easier to use, and more efficient, like the ability to know where I am in the world, people want more of it. And a good example is that map, right? The innovation of that I can know where I am using a phone. How many applications now exist that build upon location? How many people in this room support those applications, right? And it's that innovation, that efficiency of just location that has actually created a whole bunch of other innovations on top of it. And that's what's critical here is efficiency is a thing for us. So if you're a technologist in this room, raise your hand. And I'm going to do a lot of the raising hand things. You might just get used to it. I like interactivity. So you're completely useless. I'm a technologist. I'm completely useless. You provide zero value unless you actually make something happen. Technology by itself does nothing. It's cool, it's nice, but if it doesn't tell me where I'm at, if it doesn't tell me what my bank account says, if it doesn't tell me some cool restaurant I want to go eat at, or something like that, it provides no human value to me. Technology in itself is an efficiency game. The more we make things more efficient, we make it easier to do cool things. We actually improve the human experience. I hate using that language because it gets way overused, but it's the truth. And the more efficient we do that, the more efficient we make things easier to consume, the more people will want it. And the more things we can do on top of it. We actually push innovation forward. So with that, I want to talk about DevOps. Who's heard of DevOps? Okay, yeah. Again, I'm on the West Coast. The further east or central I go in the United States, the less hands go up on that one. So DevOps, this is DevOps right here. That's DevOps. Because somebody somewhere's got one of these. They've got wires, even Google. They're smart, brilliant. They still got some of this stuff somewhere, right? And this is the problem, is things aren't always easy from a technology standpoint. We're always fighting complexity and changes and all kinds of stuff. And DevOps is the idea that we started with something like this. We started with just like, hey, I now can have a server myself, and I can put an OS on an application, and I can put it in my broom closet. I can put it in my bedroom, or I can put it down the road at a colo, and I can deploy web servers. I can deploy things I would want to use, or I want to surface up like applications or other stuff like that. And that caused everybody wanted one. And then all of a sudden we have tons of these things everywhere. And then we said, hey, we're going to do something crazy. We're going to start putting VMs on this stuff, make them even denser. We're going to stack these things with more instances of applications. And then people wanted more of that now. And pretty soon we have a humongous data centers full of virtualization and VMs. And then we took databases, and we made databases. Start out with a simple database. I just want one simple little, I can mention some really old Fox Pro stuff that my dad used to use. But we got one simple little database. And then we said, oh, I want to replicate these databases around. And I want to move them around because I want to have read-only availability here, or failure, or HA. And then NoSQL comes along. We start doing some really crazy stuff, where we have databases that can literally exist around the entire world. Now, this question's for the people that are maybe a little older. How many people here would have believed 20 years ago that you could provision a database that would wrap around the entire world using Puppet on a cloud provider in one click? It's been really hard to grok back then, right? But that's reality right now. And then the world has changed in the ability for us to deliver that value and that efficiency. The problem with that is we need tools to help us manage complexity. And so tools have emerged, Puppet and Chef, Ansible, SaltStack, to help us manage configuration management and the complexity of this stuff. Because we haven't made it any easier. We've gotten more of stuff. And it's sometimes harder to run. And out of that, we have this idea of DevOps, which is a cultural change on that. What we really want, if you really distill it down, is the idea that a system administrator or engineer can run more than just one, more than just 9, but they can run many different instances of complex architecture. And that's what DevOps truly is about efficiency. So we're pushing for efficiency in that one person can do more and deliver more technology to people so that we can actually consume more of it and get more value out of it. And that's also the other part of DevOps. And this is a Puppet. Puppet has t-shirts that say this, and it was always one of my favorite things. The idea that we can deliver technology, we can deliver powerful stuff as technologists, and we can still be at the bar by 5, having fun and enjoying our lives. That it's not an endless push to kill ourselves for the ever-increasing demand and complexity of the world. We get smarter and better and stronger at what we do. And so I want to talk about one other thing. Anybody familiar with the 2-body, 3-body problem in physics? Cool, awesome. So don't correct me if I get it wrong. So there's this thing where if you have an object, and you take another object, and you want to calculate, let's say with a force of motion like gravity, how these objects are going to behave, you can do that. There's a formula. You can go run it through there, and you can say, I know how these things will behave. What's interesting, though, is that problem goes out the window the minute you add a third body or above. And for me, I was reading some stuff about this recently, and I started realizing that a lot of the stuff I'm seeing out of CoreOS and Kubernetes, stuff that's coming out of Google, a lot of this I realize is the reduction of complexity. And if you look at configuration, things that you deploy are like these objects. They have motion, right? They don't stay the same. They move, they change, pieces change. And you have to keep track of them. And so if you took these things and you think about them more like pieces of a configuration, like databases, OSs, VMs, if you only had a couple things, it's pretty easy to figure out what the state of they are in at any one point in time and figure out how to control them or configure them or manage them. But you start adding more and more and more. We start getting stacks. We start building tons and tons and tons of stuff. Ooh, check out this. Oh, check out that. And it starts to look like this. And it gets really, really complex to figure out where my things are, where they're at. And this is why in the DevOps space, configuration management is so big and declarative stuff is so big, is the ability to control an ever increasing and more complex environment gets harder and harder and harder. Which is why I like, personally, what CoreOS has been doing. And the idea is that we don't need as much as we have, in a way, right? And there's patterns from mobile industry and from other places that we can reuse from a system administration engineering standpoint. The idea that if I need my OS to be at a different version than it is now, I just throw away what it was and make it a new and redeploy things. The idea that state and clustering is higher. And there's technologies that emerged out of this. Of course, CoreOS is amazing, but you got stuff like Kubernetes as well. There's this specific stuff about Kubernetes, if you haven't looked into it, where they talk about avoiding the complexity of dealing with stuff like NAT or other things by using a pattern that removes it. So it's the designing of the system in a way that cuts the complexity out. You actually reduce complexity. So you reduce the amount of bodies you have to deal with in motion. And stuff like etcd. The idea that you can have a distributed consensus protocol on top of a database with key value store that is manageable, that you can deploy in small cluster sizes. We all know Google's got amazing distributed engineering people that are running way bigger scale than we're talking about. And I love the thing that Alex was talking about the Google infrastructure for everyone else. And that the idea is there are patterns that Google's already proven. They broke the ice on this. Tim, don't answer this. How many people here know what Google claims they do a week in containers?
2 billion.
I don't know who that was, but that was hilarious. Thank you. 2 billion. So if I'm a shop, I'm an enterprise, and I want to run a 10,000, Google's already told me that the end of this limit is 2 billion. It's feasible. And they've been doing it for years. And so the idea is exactly what Alex was saying, that what can we take from what they've broken the ice on, what they've proven, and reuse internally in our own data centers or on our public cloud or on top of other public clouds. And I think it's fascinating. And so Tectonic for us is an awesome, innovative edge to where we can become more efficient in our data centers. And a part of that is, so I run a team that likes to do innovation and kind of prototyping. And so we dived in and said, hey, could we do some cool stuff with the Tectonic stack that would make a difference? Could we do something interesting with it? And the first thing we looked at was etcd. And we said, hey, etcd is amazing, it's awesome. It's obviously got some really cool features we love. And a little known fact is me and a couple members of my team are secret lovers of distributed computing papers and protocols and stuff like that, so we read a lot of them. One of the guys on my team, Dan, who's standing there with his arms crossed. Wave, Dan. He reads like a paper a day. He's in love with them. And so we said, okay, if we were to take etcd and figure out how can we help it scale, or how can we make it more performant, how can we help in this space, what would we do? So we started looking through etcd, and what is etcd? So you can really get a much better overview of this from CoreOS, but I'll give you an overview of our thought process and how we attacked etcd and looked at ways to improve it. So etcd is a product where you have a key value store, so you have a set of nodes, and you run a distributed key value store on top. Your key values can look like that, right? Real simple data, not a lot of relationship stuff between, no linking, it's not relational model. And it uses a thing inside the RAF protocol, which it's based off of. It uses an idea of terms and indexes, which I don't have to go into detail here. The thing I want to illustrate is the indexing piece, because it's important to the next part of our conversation. And this is what it looks like. From a hierarchy, from a standpoint, if you don't want to dive into the paper, you've got this idea in your cluster, there's a leader and there's some followers. And the leader's responsible for taking on all rights. I want to write something. So if I go back to here, coffee is good, beer is better, tequila is muy buen. If you go forward, inside of those entries, those are those rights. Those are the things I would like my cluster to know about, right? And the followers are the other nodes in the cluster. They want to distribute these things too. And the goal here is to have, of course, stability, consensus, and you'll have better scale. And this is what it does. It sends each one of those entries out to each one of its followers. It's a real simple overview of the protocol, by the way, so read the paper. And then you need to choose a quorum out of those nodes. So real quick, what is a quorum for that leader? How many of those ones at the bottom do I need to have a response from that would be quorum? It's just a quick question. Huh?
2.
2? Yes. Yeah, there you go. Yeah, it's 2 plus that one. Sorry, I like to catch people on that one. So out of these nodes, if I have these 2 respond right here, and plus me, I've got a majority of the nodes, right? And that gives me consensus. The problem with this is that's a race. And in a race, you have your fast horses, and then you have your slow horses. And so if I were to send this out to each one of my nodes, we were looking at the performance of it, and we realized that at any one point in time, a node could be doing a snapshot operation, it could be doing different things, so your performance is always going to be completely uniform across the nodes, which isn't a bad thing. But we were really exploring at the 5 node, when you push etcd really, really hard, you can actually make it fall over a little bit. And we try to figure out why does this happen and how can we improve it. And so what happens is there's this concept called broadcast time. And the broadcast time in the paper, in the draft paper, is talking about basically the longest poll. So when the leader sends out its group, it's sending out to all of these nodes, but it only has to wait for these red ones to respond, right? And so the longest amount of time is the round trip time for how long it takes for that write to be acknowledged. And so at 140 milliseconds, that's cool. And what we discovered was if you take a 20% chance, or whatever percent you want to pick, and say, if I go pick a node and say at one point in time, he could be doing 5% of the time he could be doing a snapshot, maybe he's surfacing a whole bunch of reads, but there's going to be varying organic workload on each one of these nodes. And if you go look at it, some of these nodes may be really, really, really busy in a snapshot. I call them my Mr. Ed nodes. And the Mr. Ed nodes are interesting because if I have just a 3-node cluster, the problem I get is I only need to pick one. Well, if I'm racing those 2 nodes, what's the longest I'll wait? The fastest node, right? I'm only racing 2 nodes versus each other. Okay, well if we go up to a bigger node, all of a sudden my odds get worse. Because remember, it's the slowest node out of the minimum for my quorum that I respond on. So even if that first node, that first F is super, super fast, if I have to wait longer for the second one, it gets slower. Well, that problem gets scaled up quite a lot. And the reason we went through this kind of analysis is we were looking for, is etcd a database that needs help on writes, or does it need help on reads? Where is the weight? Because usually in a database, when you design one, you put the onus on one side or the other. And from the stuff we were looking at, it was obviously here. And we actually dive into this a bit more. Right majority is at the mercy of Mr. Ed, by the way, was my term here. So whatever your slowest node out of your quorum is. But if you get down underneath the covers here, you take the broadcast time and your entries, this is what's happening to each follower, right? So each follower is getting this stream of here's some entries I want you to write. They all come inbound. And the way etcd works is it streams them to everybody, it waits for an acknowledgement, and then it says, okay, at this point I know which ones are where, and then it can actually say, okay, at a certain point in time you can commit this to your state machine. And so this is what it looks like underneath the covers. It's inbound, and then it writes it to stable storage. So a node gets an entry. So DOS here is a node, and he gets tequila's good, which is his actual belief in life. And he's got to persist that to disk before he can respond back to his leader. Now think about each one of the guys doing this. Where's the bottleneck here? Want to guess? Where? Disk, right? And this is what we discovered was there's a lot of chatter to the disk because each one of these entries, those entries can have a pretty good sized batch, or they can be down to individual tiny ones, but you pay the same overhead per entry. And it can depend on the disk. If you're an SSD, maybe you're paying 250 microseconds, 300 microseconds. If you're on a SATA disk, or if you're on a public cloud on a lower end tier, you're paying a lot more. And so we said, wouldn't it be cool if you could do this? What if on the inbound, who here's ever worked with storage before? Storage market, storage arrays, SANs. Does this look familiar to you? Caching. Technically it's a buffer, because caching is technically, you gotta hit a cache also. So in technical storage terms, this is a buffer. But the idea is to coalesce the writes as they come in, and then write them to storage. Really simple concept. I didn't make this up, I didn't invent this, this is used everywhere. But we said if we apply this, how can we do interesting things? There's a problem with this. Any of my Raft experts know the problem with this one? Well, I say it louder. Yeah, so if I put it in that buffer and then I tell my leader that I've got it, the protocol says I was supposed to have committed that to stable storage. In fact, there's lots of places in the paper that you look at, it's very specific on the expectation. Nominally, the expectation is it commits to stable storage. So we looked at that and said, man, wouldn't it be cool if we could make a segment of memory used for buffering stable enough? And it turns out you can. And what we do is if you have an Intel server, which we make, I don't know if I was clear on that part. And then we have a thing called the Intel Management Engine. You put a Linux operating system on top and physical memory. If you could say, you know what, there's a small piece of this memory, physical map of memory, that you can expose logically through the Linux OS that I'd like to have persistent. I'd like to make sure this is safe and stable. And so you take this memory and you would use this as your buffer on your follower node. And what you would do is the same pattern. You'd have inbound entries from your leader. They would then get into the buffer. At that point in time, once they're in the buffer, you'd acknowledge them back. And then on certain boundaries, however big the buffer is, you'd flush the disk. And that way you would coalesce. And so you would reduce the amount of writes before you write to disk. So what happens when loss of power, kernel panic, or a crash signal? Without persistence, what would happen? Everything inside that middle box is what? Toast. It's a good description. It's gone. I can't retrieve that. And that's the problem with stable storage. We have a technology called asynchronous DRAM self-refresh, ADR. And we in the lab have got a concept working where we can actually expose the ability to, on loss of power, kernel panic, or crash signal, we can actually grab that segment of memory, pull it down, persist it to disk, and then on power on, put it back. And what's really cool about this is we can actually return those entries to disk, map those to a location, and then the next time you start your service, it can actually go pre-fetch those and restore them right back to the buffer. And this is what we were doing in our lab. And so the cool part about this is we can actually expose this through the Linux OS and through Linux APIs. But we can even drive that higher, we think, into Golang libraries. And you can do things like, I want this big of a segment of memory that I'd like preserved, and we call it refreshed, right? Because what we're doing is on power down or loss, where actually the system got enough life in it, it can actually grab stuff before it fully goes down. It can actually preserve that state. And what's really cool about this too is you can actually say where on disk you want those files to go. You can do a file format issues if you want to. You could even technically put it back into the same spot of memory into a different part of memory as well, which gets a little more complex. I'm thinking the use case on disk makes it a little easier. But ultimately, once you do this and put it back in memory, when the node resumes, he's right back to where he started. So, does that sound cool? Yeah? So, right now, these are the features. Without needing expensive battery backup, you can be orchestrated through Linux or Windows, be exposed directly into libs for stuff like Golang, and we're using silicon features that are actually a pretty normal thing to find on most E5 and above servers. This isn't some feature that you have to have a special server for or have an E7 only. It's actually a pretty common feature. Does anybody know where this feature came from or why it exists? Anybody want to guess? What industry liked this feature? Well, RAID was right. The storage industry. You know how long the storage industry has been using these kind of features? A long time. And that's what's really interesting about this. I'll get into a second about how distributed computing and kind of the emerging stuff. I'm wondering what other kind of technologies we can find were in use by other enterprise things that can be reused. So this is all cool, but does it make a difference? So what you really want to know is, did we test it? No. No, we didn't test it. No, yeah, of course we tested it. So this is a test of us running etcd, 5-node cluster on some decent hardware. And in fact, we have some decent hardware over there I'll talk about in a second. And this is about what you will run into from a transactions per second standpoint. Now, of course, depending on your hardware, this may be different. What I'm doing is baselining 2.1. So this is vanilla 208. And we topped out at about, what, 5K transactions per second. Really important thing, and I don't want to hop off the stage. You guys see this little green line right here? Everybody see that? Nod if you see it. That's errors. We started getting 500s. We started pushing it too hard. We started getting 500s. And it's well documented that if you over push a smaller node etcd farm, you can actually cause it to have errors, to start responding with errors because it can't keep up. And this is our response time graph. And the times match on both of these so that you can look at one piece and see it matches to the other piece. And you can see response times go way up. Now what we did in this test, by the way, is we were creating transactions in load, and then we would step it up, and then we would step it up, and then we would step it up. And so you can see when we stepped up, we couldn't go any higher. And the latency spiked way up. And then right when we started getting errors, we actually stopped the test. Okay, so this is 208 vanilla. This is what you can download right now. So now let's turn on our ADR and write buffering. What we did is we wrote a patch which implemented the buffering on top of our hardware. And it didn't work, apparently. That was awesome. And this is what it looks like now. You guys remember what it was before? Barely 5. And this wasn't our best test. This was the more conservative of them. We ended up getting an insane amount of more transactions through etcd. But that's not even the cool part. My favorite part is that. Response time was way better. It was stable. Now remember, we're stepping up. And at 10K, we were still staying well underneath 400 milliseconds, averaging around 300 milliseconds per. In fact, if I look at the numbers, it looks like this. Unpatched, around 600 milliseconds before we started crashing and having errors. Patched, 300 milliseconds, and we didn't actually have enough hardware to knock it over. We have to go back and figure out, can we still knock it over? How much do we need to knock it over with? And it was extremely stable. It was able to handle the burst and the load a lot better. I think from a transaction standpoint, it was close to 2 times better. Now again, we have a really heavy write mix in there as well. So if you're using etcd where you're doing very, very few writes and a whole bunch of reads, you may not see the same performance impact. If you have something where you're doing lots of changes, and unfortunately, we didn't have enough time to test Kubernetes with Tectonic. We're working on that now to actually get to a load of spinning up containers and different things like that. And this is all lab work, right? And so our goal here is we're exploring ways we can make things like this way, way cooler. How am I doing on time? Oh yeah, I got tons of time. All right, so raw numbers from Prometheus. So if you guys don't know, on the master, CoreOS has started to integrate Prometheus, which is a monitoring framework. It's actually kind of an application monitoring framework in Go. And we actually took some of the stuff from master and dropped it into our patch so we can actually capture some of the numbers on syncs to disk. And before patch, it was, in a load window of 101 seconds, it spent 25.8 seconds writing to disk. That's insane. It's amazing it can do that, actually. And then with our patch, we reduced that down to 1/3 of a second spent writing to disk by using that memory buffer, which is awesome. And that's why you're seeing that huge scale and performance increase. And all we're really doing right there is we're using some cool hardware stuff to hit a hot spot and try to accelerate this really cool software. That was my reaction when I first saw it. Do people know who that is, by the way? I'm really curious. Who said Barney? Okay, cool. We got a couple. Couple out of like a full room. Okay, so disclaimer, patch is still working. Our goal is to actually work on this some more, stabilize it, and actually, we showed CoreOS this, and we want to get a cool pull request open. We think we should expose this as a feature so you can turn this on. Whether you have the hardware piece or not, you can actually explore testing this out yourself. And so our goal is to upstream and open a PR for review, explaining and walking through all of our stuff, and adding some cool flags on the etcd CLI so you can actually, when you start a service, you can turn it on or off, or change the size of the buffer and stuff like that. So this begs the question, if we could do, we did this in like 3 weeks, 4 weeks of work. If we could do this for this, what else could be done? And from an Intel standpoint, we're really curious about distributed systems for everybody else. And there's stuff like, we're already exploring the idea of LSMs, like log structure merge trees, the ability to have even the writing to the wall log to the disk be even more performant. Like, could I put hotspots? So if I have, let's say I have Kubernetes, and Kubernetes tends to hit certain key spaces heavily, and other ones not so heavily. Could I put etcd on a piece of hardware or on disk in a way where I can actually put the hot volumes? Who's ever run databases before? How familiar does this sound to you? Really familiar, right? So we could do that. Network acceleration with Rocket and Kubernetes. Intel does a massive amount of work on x86 acceleration for networking. What can we do there? Golang acceleration. Golang is a powerful language. What can we do with Golang and accelerating and making that faster and more secure? Future offloads for distributed systems. If you've got really good ideas on ways that we can actually offload and make things faster in a distributed system, we're all ears. Because this is what we do, is we find ways to make our hardware valuable to software people. Security at the OS container and the wire. What kind of security protocols can we contribute to? What kind of container pieces and specifications need more strength from a hardware standpoint? And then telemetry exposure for schedulers. We're big on this. We figure if we're going to go down the scheduler route, the scheduler is only as smart as the information presented to it. So what could we share? Does anybody ever pull like power and thermal stuff from an Intel server? Like hardcore power and thermal stuff? A couple of hands. Most of you haven't. So I happen to work on a group where there's like people with PhDs on power and thermal on my team. And I talk to them and I'm like, there's a whole world of stuff I didn't know existed. And what if we could expose some of that stuff and actually put it in schedulers? What if we could expose it in a way that was actually useful to you, right? And you didn't need to be a company that has 100 data centers to even be in that conversation. And I think from a scheduler standpoint, it's an interesting area that now that this exists, there's an opportunity for us to go do interesting things. And a lot of this data already exists, you just don't have access to it. And we should go fix that. So distributed systems for the common man. See, I wrote that, and then he said his thing. His is way better. Google infrastructure for everyone else. But that's kind of the point here is we have spent at Intel a lot of years, which I don't get credit for because I'm new at Intel, accelerating lots and lots of stuff. Who runs virtual machines? I've run virtual machines. Virtualization runs on top of a lot of core technologies that Intel helped develop with other hypervisor companies. And what can we do for distributed systems? What can we do to accelerate and make them faster and better and easier? From Google scale all the way down to the mom and pop shops. So, Tectonic is awesome. It's the ability to go, and as a person that's everybody else, like he says, to go pull something down and play with and explore and try out Google's infrastructure at home. And we thought, wouldn't it be cool if you could do that? And so, a couple guys who work on the lab stuff had a trip yesterday, or the day before yesterday down here. Turns out that if you have a bunch of equipment you want to get it to San Francisco, if you wait too long, it's not going to work. And so they went and got a van and literally drove a whole bunch of equipment that's sitting over there all the way down. I love this right here. Dan, he's really good with pictures and emoticons. Maybe he can translate what my daughter's sending me. And this was them yesterday trying to load it up. Turns out when they got here, they had no way to get it off. It's like 1,000 pounds of rack. They had no way to get it off the van. But they were to bum it off some guys that had an elevator rack. But sitting over there is a rack of Supermicro Intel servers that is running Tectonic. And today, Intel is announcing we are going forward with a partnership with Intel, Supermicro, and Redapt so that when Tectonic becomes GA, we wanted to make it where you could order and get shipped to you a rack ready to go, built and designed. And this is really, really important because remember all that stuff I just talked about from a lab standpoint and acceleration standpoint and feature standpoint? Remember all those things I said we could go do? All the things we could go partner with Google or go partner with CoreOS on to make things faster and stronger? Guess where it's going to all be able to land? And that's what's cool about this, is we can also commit to the fact that if we figure out really cool ways to make this stuff faster, we can put it into a place where you can get access to it really, really easy. And so we're announcing this today that we're going forward, and when Tectonic GAs, you'll be able to order this thing, and you'll be able to work with guys like Redapt to come help it land in your data center or in your broom closet or wherever you want to have it and get it running quick. So you can go see it at the booth right over here. We actually have the equipment here running if you want to go see it running it. And thank you very much.